In this unit, we're going to talk about translations of functions, and the functions that we're going to focus on are these 7 here. So the first one is a linear function. So in order to graph that, we can complete the table of values just for y equals x, the basic linear function or parent linear function. And then we can plot those points. You should have an idea of the shape that you're expecting. And then if you're plotting a line, you should always use a ruler. There we go. Okay. So the domain, or all the possible x values of a linear function, is all real numbers, or we write that as minus infinity to positive infinity. The range is the same, all real numbers, negative infinity to positive infinity. When you're graphing this, the features that you need to be familiar with or to look for are the slope and the y-intercept. Those are the key features of a line. And let's move on to the next one, the quadratic function. So same thing, we're going to complete the table of values initially to allow us to graph it. And we've got our parent function of the parabola, y equals x squared. Obviously, there are many other types of parabolas, but this is the base parabola or the parent where the rest of them start from. So our domain here in this particular parabola is going to be all possible x values from minus infinity to positive infinity. And our domain here is from 0 and everything above that. When you're plotting a parabola, the key features that you want to look for are the vertex, the zeros, and your direction of opening. That is what's going to allow you to distinguish your particular parabola from any other. Okay, moving on next to a cubic function. And here we're going to start off with our table of values. So for y equals x cubed, we've got minus 27, minus 8, minus 1, 0, 1, 8, and positive 27. And we can put that on the graph. Looks a little bit different than the parabola. And we can connect those points. So our domain, again, just like the previous two, is all possible x values, so from minus infinity to positive infinity. And our range is going to be the same, minus infinity to positive infinity. We don't have any values that give us any trouble. Now the features of a cubic function is that they do have don't really have a vertex, okay? They do have a point of inflection, which is right in the middle, right here. The ends go in opposite directions. And then we've got that this is actually, so this is curvier than the line, but similar in the sense that the ends go in opposite directions. So let's move on to function number 4. This is the absolute value function. So the absolute value just means that whatever value you put in, you are going to get the same number, but positive. So filling in our table of values, 2, 1, 0, 1, 2, 3. And then we're going to plot those points on the graph. So 3, 2, 1, 0, and then the same in the other direction. And this particular one looks like a upside down triangle or a V shape. Our domain, just like the previous ones, is minus infinity to positive infinity. Our range this time is all the values 0 and above, sort of like our parabola. So the features of this graph is that it does have a corner point. It's not a curve like the parabola. And all our y values are positive. Okay, so moving on, we've got 3 more graphs. The next one is the exponential function. So y equals 2x. Filling in the table of values here, we've got 1/8, 1/4, 2, oh, we've got 1/2 here, sorry. And then we've got 1, and we've got 2, and we've got 4, and we've got 8. So now we can fill those in on our table of values. So we've got 3 and 1/8, so pretty close to the x-axis, minus 2 1/4, minus 1 1/2, 0, 1. And then continuing on, we've got 1, 2, 2, 4, and then 3, 8. Here we go. Okay, and connecting those dots, now we can see that our domain, just like the other ones, is minus infinity to positive infinity. Our range is going to be 0, not inclusive, all the way to infinity. So the features of this graph are that we've got a horizontal asymptote, which means a line that the function approaches but never touches. Okay. It's also not symmetric, which is different than the other ones that we've looked at. And we've got a point here at 0, 1, which is kind of our key point right in the middle. The next one is a square root function. So we're taking the square root of our inputs. So filling in our table of values and plotting that on the graph. 1, 1, 4, 2, 9, 3, and then 16, 4 up there. And I'm going to connect them going up like this. And then I'm going to state my domain. So I can see from my graph that I have all the values to the right, but starting at 0. For the range is the same thing. I start at 0 and then anything above. So this looks like half a parabola. Okay, that's kind of its distinguishing characteristic. Okay. The last parent function is the reciprocal function, which is y equals 1 over x. And so here we can take some time to fill in our table of values here. Minus 1/4, minus 1/3, minus 1/2, minus 1, minus 2, minus 4. Now we've got 1 over 0. We know from our work with restrictions that that does not exist. Then we've got positive 4, 2, 1, 1/2, 1/3, and 1/4. So that's going to be a lot of points to plot, but that's okay. We do have 2 asymptotes actually for this function, which go right along my axes here. And I'm going to draw those on in a different color. I'm going to use red. So asymptotes, we're always going to draw on with dotted lines. They are aligned, so they do have an equation. So this one here is going to be x equals 0. And then kind of like in the exponential function, there's no value that we can put in for x that's going to make y equal 0. So that is our second asymptote. Okay, they are equations of lines. Okay. And then we're going to take some time to plot our points here. So minus 4 1/4, minus 3 1/3, minus 1 and 1. And I skipped minus 2 1/2 there. Okay. And then I also have some points in between 0 and minus 1. So I've got minus 1/2 and minus 2. And I've got my points in the wrong spot here. So let's retry that here. Okay, so minus 4 and minus 1/4 is just going to be underneath the x-axis. Minus 3 1/3, minus 2 1/2, minus 1 and 1. And then I've got minus 1/2 and minus 2, and then minus 1/4 and minus 4. And so what I can see is that these points are going to go down closer and closer to the y-axis, approaching 0. And then they're going to get closer and closer to y equals 0, going in the other direction. So let's plot. We've got a second half of our graph in the positive quadrant. So I've got 1/4 and 4, got 1/2 and 2, 1 and 1, 2 1/2, 3 1/3, 4 1/4, and I've got almost the same pattern just on the other side. So in this one, this is the trickiest domain to do, but our x values go all the way from minus infinity to 0, not including 0, and or the union of all the values from 0 to positive infinity. Our range is similar. We've got minus infinity to 0, and then from 0 to positive infinity. And the key features of this graph, as we already mentioned above, are that we've got two asymptotes, y equals 0 and x equals 0, and we've got really two distinct sections of the graph. On the last part here, there are just two reminders of what an asymptote is and a discontinuity. So a line that a curve approaches but never touches is called an asymptote. And we can say that, for example, this graph is discontinuous at x equals 0 because there is a break in the graph. You should be familiar with those 7 parent functions, their shapes, their domain, and their range.